welcome to this video in which we will learn the method to solve homogeneous linear differential equations with constant coefficients. So guys, consider an second order linear homogeneous differential equation with constant coefficients a y double prime plus b y prime plus c y is equal to 0, where a b c are constants and y is our unknown function, and y prime and y double prime is the first and second order derivative of that function. So guys, we will assume our solution as y is equal to e raised to power mx, and this solution will eventually converts our differential equation in the form of a polynomial equation, and that polynomial equation will determine the structure of our solution. So guys, we have three cases in this method. So case 1 will cover if we got the distant real roots of our polynomial equation. Case 2, where we will get the same repeated roots of our polynomial equation, and case 3 will cover if we got complex roots for that equation. So now we will take examples, each example from all these cases. So first off, we will cover case 1. So let's consider a differential equation of the form y double prime minus 5 y prime plus 6y is equal to 0. As I told you earlier that we will always assume our solution as y is equal to e raised to power mx. So we will take the first derivative of y, and y prime will become m e raised to power mx, and y double prime will become m square e raised to power mx. After substituting these derivatives, we will get m square e raised to power mx minus 5 m e raised to power mx plus 6 e raised to power mx is equal to 0. We will take e raised to power mx as common, and we will get m square 5 m plus 6 as the leftover. So we know that e raised to power mx can never become 0 because this is an exponential function, and an exponential function never gives 0 for any value of x. So m square minus 5m plus 1 will become 0. So we will solve this quadratic equation. So we got the plus 6, sorry. Now we will solve this quadratic equation, and our solutions for this quadratic equation are m1 is equal to 2 and m2 is equal to 3. So this case covers the distinct real roots. So we got two distinct real roots. So in this case our solution will be the form of c1 e raised to power m1x and plus c2 e raised to power m2x. So this is the general solution for the case of distinct real roots. So now we will substitute our roots in this equation. So our solution will become y is equal to c1 e raised to power 2x plus c2 e raised to power 3x. So guys, this was the case 1 where we covered the same distant rule for our polynomial equation. Now we will cover the case 2 where we will get repeated roots for our polynomial equation. So let's consider the equation of a form y double prime plus 2y prime plus y is equal to 0. So as always, we will assume our solution as y is equal to e raised to power mx, and y prime will become m e raised to power mx, and y double prime will become m square e raised to power mx. After substituting these values and simplifying these equations, we will get e raised to power mx into m square plus 2m plus 1 is equal to 0. We know that exponential functions can never give 0, so we will put m square plus 2m plus 1 is equal to 0, and after solving this quadratic equation we will get the solution m is equal to minus 1 and m is equal to minus 1. So in this case we are getting repeated solution repeated roots. So this is a case 2. So the general form in this case will become c1 e raised to power mx plus c2x e raised to power mx. The only difference in this solution is this x. So we will substitute our roots in this equation, and our equation will become c1 e raised to power minus x plus c2 e raised to power c2x e raised to power minus x. So guys, this was the second case, and now we will consider the third case, where we will get complex roots. Sorry. So guys, consider equation y double prime minus 4y prime plus 5y is equal to 0. So we will assume our solution as y is equal to e raised to power mx, and after solving we will, so y prime will become e raised to power mx, and y double prime will become m square e raised to power mx. So after substituting these values and solving and simplifying our equation, we will get e raised to power mx, m is into m square minus 4m plus y is equal to 0. So e raised to power mx can never become 0. So m square minus 4m plus 5 will become is equal to 0. So we will solve this quadratic equation, and our roots are in the form of complex numbers 2 plus minus iota. So in this case we are having the fruits in the form of m is equal to alpha plus minus beta iota. So we are having a complex number here, and we will take our real part is equal to alpha, and our imaginary part in this case, which is 1, is equal to beta. So the solution in this case, where we are having complex roots for our differential equation, is the form of y is equal to e raised to power alpha x into c1 cos beta x plus c2 sin beta x. So in this equation, for this equation and for these roots, our solution will become y e raised to power 2x c1 cos x plus c2 sin x. So guys, I have covered all the cases in this method to solve the homogeneous linear differential equation with constant coefficients. I hope you like this video. If you want to book a trial class with me, kindly check the links in the description. Kindly like this video and do subscribe. Thank you for watching.